In this video, we're going to look at one final example of calculating a physical property from a given partition function of a system. So for a system of n indistinguishable ideal gas particles, we have this partition function again. Q is equal to volume to the power of number of particles over number of particles factorial times this whole quantity here, 2 pi, mass of a single particle, over Planck's constant squared times the inverse temperature beta, and all of that to the power of 3n over 2. And we'll remind ourselves again that this quantity beta is the inverse temperature, defined as 1 over the Boltzmann constant times the Kelvin temperature. Okay, so the physical property we're interested in here is going to be pressure, or average pressure, or expectation value of pressure, whichever you prefer to call it. And this is going to be minus the partial derivative of our average energy with respect to volume. Energy depends on not only volume, but also number of particles and inverse temperature beta. So we're going to make it clear here that this is a partial derivative with those two quantities fixed. Okay, so that's our pressure. It's kind of the response of the energy of a function, response of the energy of the system to kind of mechanical distortion of our box. It's changing volume here. The negative of how the energy changes with changing volume is going to be our pressure, and that will correspond to what we see pressure defined as in the macroscopic sense later. Okay, so we have this here. If we recall from before, our energy of our system, average energy, was defined as minus partial derivative of the logarithm of the partition function with respect to inverse temperature beta, and that would have been at constant number of particles and constant volume. And so we're taking now the derivative of this whole quantity with respect to volume. So I'm not going to show this transformation here, but with sufficient algebra you can show that you could rewrite this expression for pressure in terms of the following quantity. It would be 1 over beta times the partial derivative of the log of the partition function with respect to volume. And that would again be with constant number of particles and constant inverse temperature beta. So from now on, we're just going to kind of take this as a postulate. So this is going to be what we're going to use to calculate what the pressure of our system is. Okay, so we need what the logarithm of our partition function is, and we need to differentiate that with respect to volume. So using the same kind of technique we did in the previous videos, we can show that the logarithm of our partition function, ln q, is going to equal a term that looks like n log v plus, and then we can separate it into a bunch of other terms that don't depend on volume. So terms without volume. So because those other terms don't have volume, we don't need to worry about them when we differentiate with respect to volume. And if you're confused about where this is coming from, I show in the previous 2 videos how we can separate these when you have a logarithm of a product and a quotient of several functions there. Okay, so we have this n log v plus stuff that doesn't have v in it. So if we differentiate that with respect to volume, then we get n times the derivative of log v with respect to v, and that's just going to be 1 over v. So we have n over v, and now in order to calculate our final result, the pressure, expectation value p is going to be 1 over beta times this partial derivative of log of our partition function with respect to volume, which is just n over v. It's going to be n over v. Then remembering here that beta is just 1 over kt, so 1 over kt is just going to be kt. So we have n kt over v. But again, we need to remember that number of particles times the Boltzmann constant is exactly equal to number of moles times the gas constant, the macroscopic gas constant R. So this is just Boltzmann constant times Avogadro's number gives you R. Number of particles divided by Avogadro's number gives you N, number of moles. So Nk equals Nr. So then we can substitute this Nk here, and we can put N RT over V. So what do we notice here? This is actually really cool. We get, from calculating the pressure of our system here just from its partition function, which we got from summing up all of its Boltzmann factors, we get that the average pressure of an ideal gas is going to be nRT over V. And why is that neat? Well, if you multiply times V here, you have PV equals nRT. It's the ideal gas law. So just as should happen, if there's any sense in what's occurring here and the magic of these Boltzmann factors and partition functions, then we should get back a nice simple result here, which makes sense. So this is a nice validation that what we're doing with these partition functions actually makes sense here, because we got back our famous classical result here, that PV equals nRT for an ideal gas. So this is a nice demonstration of the power that partition functions have, and we said nothing about anything except the energy levels of the system, and we assumed the Boltzmann factor in the form of a partition function, and using only those 2 or 3 factors, you end up getting this fact here, that the pressure of an ideal gas is nRT over V.